Hello, everyone, and welcome to our seminar on SSA. So today we are very glad to welcome Professor Rizos from the University of New South Wales, and he'll talk about satellite positioning. But just before getting started, we wanted to introduce ourselves for those who don't know us yet. So we are SSA EPFL, a newly recognized EPFL Students Association, and we're doing space situational awareness. That is to say, we're trying to detect satellites and satellite debris from ground-based observations with our newly bought telescope we show in this slide. The aim is then to take images of satellites, as you can see it here on this picture, and to compute the trajectories in order to make a catalog with all the objects we've detected so far. This is increasingly important as the number of space debris is increasing, and so collisions become more frequent or can become more frequent. We also want to give like a platform to those purposes and to make the problem more known among students. This is why we started, or we want to start, a seminar series on space situational awareness. The idea of this seminar series is to give a broader view of the subject and related themes like today's lecture. So if you have any questions concerning the association, you can come back to us in the end. We'll be very glad to answer your questions. But now we are happy to introduce the speaker and then to hear his lecture.
Yeah, so we'll give a brief introduction of Professor Rizos. He comes from the University of New South Wales and is the Emeritus Professor in the School of Civil and Environmental Engineering. There is founded the Satellite Navigation Positioning Lab, and this is Australia's premier academic research group in wireless positioning in GNSS. He's received his Bachelor of Survey at UNWS in 1975, and then went on to Sydney University, completing a PhD in Southern Geodesy. And since then, he's been very active in the field of GNSS, GPS, and geospatial technologies. And his efforts and his research have been acknowledged with several awards. Also, he's very active for the community and covers different roles. A few that I'd like to mention is that are ongoing roles that is serving as. He's currently the president-elect of the International Union of Geodesy and Geophysics, and is member of the National Committee for Earth Sciences of the Australian Academy of Science. And we're very glad that he's today with us. He has a brief introduction to GNSS. So without further ado, we look very much forward to the presentation.
Thank you very much. Thank you very much for that introduction. I apologize, I have a little bit of a cold, but I hope that I will be able to still be loud enough to
It's more official. It's confirmed.
in my sort of email correspondence with the SSA EPFL team, and thank you very much for inviting me. I was trying to determine what level of understanding and knowledge the audience would have as far as satellite-based positioning. So we can talk about satellite positioning, which is orbit determination in the sort of classic sense, or we can use satellites to do position. You can do position on the ground, you can do position in the air, you can do position in space, you can do positioning on the moon using satellites. And of course, we can find other scenarios. So I'm going to be speaking about the topic that's I've been engaged with for most of my academic career, basically starting probably 35 years ago with GPS. And has since extended to what's called the Global Navigation Satellite System, or some people call it systems. So it's GPS plus the other constellations, which I will be talking about today. So the topics principally are going to be about the background, talking about the capabilities. Of course, we're talking about positioning, but we can also measure time, we can also measure velocity. But it will be principally focused on positioning because many of the applications deal with navigation in all of its forms. And I'll be therefore touching on applications, although I'm conscious that I won't have time to cover all of these topics in depth. Now, I apologize if some of the people in the audience perhaps already have done lectures on GPS and GNSS, and therefore they might find some of my material repetitive. On the other hand, there could be some people in the audience that think, well, actually, I'm moving a bit too fast, and I didn't realize it was so complex. So it's going to be a challenge. That on the left-hand side, I'm not going to be reading all the slides, by the way. I did update these only a couple of days ago because it's good to be encouraged to make a presentation for audiences every so often because it forces you to actually understand and to understand and appreciate the audience's perspective. What do they know? What have they heard about? What have they heard of? How can I relate it to their own experiences and their own knowledge? So remember I said GNSS is the politically correct way. People still talk about I use GPS. Well, hardly anybody uses GPS on its own. Maybe the US military and its allies. Everybody else, carries one of these, is using a GNSS. It's not just using GPS, as we'll see in a short while. There's more to that. The space world is full of acronyms. So we'll start to see these acronyms, and I'll try to spell them out there. GNSS, PNT, Global, Reliable, Position, Navigation, and Time. This is sort of agreed to acronym for this particular set of applications. There's Earth observations, there's satellite communications, there's SSA, there's space health, right? Astronauts in space and so on. But PNT can of course be done by satellites, but can also be done by other technologies. But today we're going to be principally talking about GNSS. So talking about satellite signals being received, the coverage, because it's global, is obviously around the Earth, continuous 24 hours a day, supporting a wide range of applications, using a wide variety of devices, systems, and services. That's where it gets complicated. If I was only to focus on what goes on in that mobile phone, easy. Well, it's hard from the signal processing point of view. It's easy from the mathematics and principles point of view because this is very basic. In my world and in Jan and Bertrand's world, we have enhanced positioning performance. We've enhanced the accuracy through adding layers and layers of complexity on what is essentially a system designed in the 1970s. The first GPS satellite was launched in 1978, right? The principles go back even earlier than that. So it's very elegant. And as far as an engineering achievement is concerned, it is fantastic. Since then, of course, we've enhanced it. Other countries, other nations, other groups have developed add-ons. So today, one of the things that I hope you'll take away from this lecture is that the world of PNT, even if you use GNSS, is now far more complex in terms of the range of methods and the mathematics and the devices and the signals than the original GPS design. Okay, so GNSS is now a generic term for, I don't know whether you know about MEOs, medium Earth orbit, inclined geosynchronous orbits, and geostationary orbits. So a combination of those types of satellite orbits going into making up a constellation or several constellations of GNSS that are used by users for position and time determination. There's also an RNSS, a regional navigation satellite system. Of course, as that implies, it is limited in geographic coverage, therefore you have less satellites and you have, in a sense, a more spotlight type coverage. They're so successful, GNSS, let's just use GNSS as the generic term, so successful it's the obvious choice for all outdoor applications. You wouldn't even think about using anything else except for applications such as autonomous driving and a few others for collision avoidance, for determining your position relative to landmarks, because GNSS provides you with a position in terms of a coordinate, right? Because with the coordinate, whether it's a coordinate here or the coordinate outside, obviously with GNSS it's easy to get the coordinate outside. But if I want to move from that coordinate to another coordinate and there's a wall between them, GNSS can't tell me to stop running through that wall, right? That's where you need your other sensors to give you a complete navigational capability, you know, a true situational awareness to allow you to do, for example, robotic type applications. Now, each of the GNSS offers several services and have unique characteristics. That's where the complexity comes in, but there's also a lot of shared features. And in particular, this statement here in bold is the one I always like to use, because I keep talking about GPS. GPS is the way that you can describe many of the principles. It was the first one, everything else is, let's not call them copies, but seeing that it was so successful and is still so successful, there are many, many characteristics of GPS which basically been reproduced in other GNSS. So if I wanted to talk about positioning using Galileo, I can go back to GPS and just tell you, okay, substitute this signal for that signal. It's a detail. The mathematics is exactly the same. And I'm only interested in the mathematics. The applications are exactly the same. Galileo does not open up applications that GPS has not already opened, and so forth and so on. Something about the orbits, again, because I assume that you people are interested in space and satellites. We're dealing with orbits which are quite far, quite distant. These medium Earth orbits are at least 20,000 kilometers above the Earth's surface. Of course, geostationary satellites we're talking about here about radiuses of orbits of, they're mostly circular orbits, of about 42,000 kilometers, to give you that one period per day. Remember, Kepler's third law gives you the orbital period. So that's a nice link, therefore, back to some old astronomy. So your customary geostationary orbits are around the equator, principally used for communication satellites, but now also used for navigation satellites. And they're ideal because as the Earth rotates, they will complete one period, so they're always over the same point. So that's how you get your spotlight coverage. But you can't do positioning from one satellite. You need a bunch of satellites. And that bird cage is the iconic image of GNSS. Yeah, it's the Earth rotating underneath, and you have the orbits inclined, medium Earth orbit. This is this sort of orbit here, with radius of approximately 26,000 kilometers. And that's the bird cage, and you can see the visibility will change as the satellites are moving across the Earth, across in their orbits, and the Earth rotates underneath it. So you have quite dynamic coverage. Right, the satellite is moving, it's not streaking across the sky, it's not a LEO orbit, it's not a low Earth orbit. It could be above the horizon for several hours, but the coverage, there's satellites everywhere. Now, the more satellites you have, the more chance that you could be standing somewhere and you will see enough of the sky, or your receiver can get signals from enough of those satellites to be able to make the measurements necessary to feed into the equations to create the output, which is position or timing. So I'll talk about some of the constellations and which mix of orbits they have. Now, there are some new PNT concepts based on LEO mega constellations, the ones that Elon Musk wants to launch at hundreds to thousands of satellites. These are wonderful for PhD topics. Commercially, they're not going to happen for probably 5 at least years. And then they'll discover how hard it is. Right, remember GPS first started was 1978, became fully operational in the mid-1990s. Since then, we've been working on refining the orbits and the errors and the biases and the signal processing necessary to basically create reliable and accurate position navigation time. To think that overnight, just because you put up a lot of satellites and you have a lot of signals, is going to make it easier is naive and obviously an attitude from those who basically haven't been in this business very long. But it's great to look at the geometry, signal to noise ratios, the Doppler effects. Try to even build a receiver, right? Open source software receiver, fantastic. But honestly, they still will only work outdoors. They won't work indoors. They probably could be jammed a lot easier, although there's a lot more of them. And their signals are probably stronger if you can get the payload on them. And that's when it starts becoming interesting, because you can't position using satellites unless you have an infrastructure dedicated to tracking them from the ground to get the orbits so that the signals are transmitting not just measurement signals, but information signals that a receiver then can lock on, measure, and decode. And that, is a huge undertaking. Short history of satellite-based positioning. In fact, it actually spans my life almost. When I was born, just before the beginning of the space age. And basically the point I want to make is, let's just start with the blue here. There was an early navigation constellation, some older professors might remember. GPS, 1978, the Russian system, still during the Cold War. It still is a Cold War. In fact, it's a bit hot now. They use GLONASS. The Americans and their allies use GPS. Others, sorry, I should go back. How do I get back? Sorry. That's right. Now, what is happening here, this one here, show the dates, is around about the turn of the century, a whole bunch of other players came in for various political reasons, mostly the political reasons. Nobody built these systems because they wanted to serve mankind, the better system, but GPS was working and it's free. Right? Sure, it's owned and operated by the military, but yeah, it's a dual-use technology. So what do we have? We had the Russians. Obviously, everything the Americans did, the Russians had to do. And like the Russians do with a lot of technology, they took a different route. Perhaps in hindsight, it was a bad route to take. But designed, operated, funded by the military. Then you had Europeans sort of getting nervous around about here about access to GPS. So they started launching the first of the demonstration Galileo satellites, Geodesy A and B. GPS got modernized, so we now have several generations of GPS satellites with extra signals being added, more civilian signals, but also more military signals. So now a modern GPS satellite has, from the perspective of a signal receiver designer, an absolute smorgasbord. They can choose whether they want the prawns or the chicken or the vegetarian option or the gluten-free and put them together on their plate, okay? That's where additional complexity comes in. So this has already been done for you. The designers of those chips have decided which of those signals they will be tracking. The Chinese system, this is the first generation we have, was launched. We're now up to generation 3 already. Everything the Chinese do is accelerate. They can manage to launch 40 satellites in 4 years. It takes the US maybe 20 years. The Japanese quasi-zenith satellite system is actually a regional navigation satellite system or an augmentation to GPS and Galileo. We have the Galileo, the initial operational vehicles, final operational capability. GLONASS was not that long ago. For GPS, it meant when they reached their full constellation to allow for 24-hour global coverage. That's what we call the final operational capability, FOC. That was the mid-1990s. We have the Indian system. Galileo. I think Galileo is still not quite there with its final set of satellites. So if you look at it in terms of the Earth and distances away from the Earth, you can start to see where some of these satellite constellations are. We'll see these acronyms later. SSA, Space-Based Augmentation System, the New Regional Navigation Satellite System, the quasi-zenith satellite system, blah, blah, blah. Okay, 42,000 kilometers from the Earth center approximately. This is the MEO world, GPS, GLONASS, Beidou, Galileo. Down here is the Earth observation and the LEOs and things like that. So they're substantially, they're not contributing to space junk. Okay, that's the technical message. We have the four what we call global constellations: GPS, GLONASS, Galileo, Beidou. Right. The current number of satellites and the planned number of satellites, and only Galileo is not yet there. We have regional constellations. The Indian one, now called NAVIC. And I forgot that acronym, so please don't ask me that. Somebody maybe remembers what NAVIC means. There's the Japanese one, which currently is up to 4, but we'll move to 7. And there is, a whole bunch of other stuff down here, which I'll be talking about. These are examples of the extension of the capability of standard GNSS. So you take GNSS as your basic technology and methodology and so on, and then you can add things to it. You can augment. So the word augment means to somehow improve performance measured in sort of different ways. If we look at now in terms of the number of satellites, not that are visible anywhere, but just the total number of satellites, because not all of them can be visible at the same time everywhere on the Earth. Okay. Remember, the whole reason why we have multiple satellites is that we'll have enough satellites visible everywhere, even with lots of trees and buildings, but not everything. There's also a huge amount of duplication. You've got to appreciate the US military is not going to use the Russian system. The Russians are not going to use the GPS system. So you can't tell Russia not to launch more satellites because we don't need them. You can't tell the Chinese government, sorry, we don't need any more Beidou. You can't tell the European Union, stop wasting your money. We don't need Galileo. So each one of them will find a reason to continue to fund it. And every one of them will slide, can be challenged on the EU, is funded for military or security purposes. Okay, so we're now about here. Oops. I've made a statement down here because also from the perspective of those who design algorithms, like myself or Jan or Bertrand, the more satellites you put up, the more signals you put up, the more errors there are, the more complex the modeling, observation modeling. So in fact, it's creating work for those who want to design more complex algorithms. Not that it was set out to do it that way. I mean, there are advantages to having what we call multi-GNSS. Now, I did this calculation for Lausanne for today. I'm not sure at the time it was UT. This is the number of satellites bin for every hour, or every half hour, every hour. The number of satellites that are visible above 10 degrees elevation angle. So this is not right down the horizon, it's sort of like 10 degrees looking around. This is supposed to be at 4 o'clock ET. I don't know when that is here. My mind's not functioning currently. But you can see that we've got substantially more than 30 satellites. And in fact, we only, in theory, need 4 satellites to be visible, 4 independent measurements, to give you basically a solution, unique solution for 3-dimensional coordinate, X, Y, Z, latitude, longitude, height, and time. So there's a substantial redundancy. And here we've got the number of satellites that are different color coded and so on. And this website, for example, does the calculation for you. Now this is a sky plot where the outer circle is the horizon. And I've got the 10-degree circle there. And this is where all the satellites are. This is the zenith. I don't know where north is here. Yeah, it's north that way, north, okay. North, east, south, and west. And the different circles represent different elevation angles. So this is a snapshot, sorry, at the 12 o'clock mark, for the 37 satellites that were visible. So if you're standing next to a building which is totally blocking, like you're out there and you can't see to the south, you only get that patch of the sky to see. In principle, you have enough still to navigate. So if you're a soldier in an urban area, we won't mention where right now, you will still, if you've got a patch of the sky, you will be able to get enough satellites to get a solution. Now, how good that or how accurate it is, it's another matter. We won't dwell into that. Now, that's part of the story. That's just the number of satellites. And I said before, each satellite transmits, not necessarily a smorgasbord, it'd be hard to use that as a metaphor, sends signals on multiple frequencies. Now, these horizontally, this plot here, are the different constellations, all essentially what's called the L band, microwave band. So the wavelength is about this much, varies depending on the frequency. And have designations such as L1, L2, L5. The Europeans have a different coding system, E1, E5, E6. The Russians have a different way of designating them. The Chinese also have, they call them B1, B2. So it's not even a standardization, but what has happened is that quite a number of them, in fact, almost all the constellations, agree that they should be within or pretty close to the central frequency, what we call the L1 band and the L5 band. And it's not by a mistake or by them being in agreement, but these are actually, from the ITU perspective, the International Telecommunications Union, these are protected bands for the aeronautical radio navigation services. So if they wanted certification for use of these signals, or these systems, I should say, for civil aviation, which everybody wants to be a good global citizen, then they have to be able to transmit open signals on the L1 and the L5. So this is your base model should be able to track these two frequencies on the open signals. Now there are encrypted signals in here. There are encrypted meaning sometimes for commercial purposes, sometimes for military purposes. And these are a spread spectrum and not a digital signal processing person, so I'm not going to explain to you very quickly how you can create that, but basically you have a sine wave, you modulate it with a digital code, it spreads the spectrum, and it actually allows for the transmission and reception even with very, very low signal to noise ratios. But basically, the people that want the highest fidelity, professional scientific users, want to track as many of these signals as possible. Because with every tracking signal, you make a measurement of distance. And you've got 30-odd satellites visible. You have a massive redundancy, massively over-determined system, and you therefore can drive the accuracies down. But to get access to all of those is sometimes not possible. There are digital signal processing tricks to even track an encrypted signal to make some measurements of what we call carrier phase. But if you want to make it according to the textbook, you have to know the key. So the analogy is basically the key is what you have. In fact, you have a lot of keys, public, you buy the documents, download the documents. You have multiple keys, and in some way you can imagine these components of the transmitted signals are different locks. And in some of those locks, your key will not go, therefore you cannot use that signal to make a measurement. In some of them, it will go. And pushing that key into the lock is also a way in which we match the cuttings or the imprint in the key with the imprint that's inside the lock. And with that, we're able to make a determination of a distance. I mean, it's a crude analogy. This is a Huawei smartphone. And I said, currently, it actually, if you look down here, look at all the satellite signals, not just satellites with their little flags, right? We've got the 4 constellations there, even the Japanese, of course. We've got L1, L5, L1, L5, L1, L5. So there's actually 1, 2, 3 satellites, but in each of those satellites, there's 2 measurements to be made of that smartphone. The same goes down here. The China, this particular one only has B1. Probably the next generation will also have B5. Got the L1 and the L5. Not all GPS satellites transmit on L5, so that's not a complexity that I don't want to necessarily deal with. But in the process of renewal of different generations, you will get legacy signals and new signals, and things get a little bit messy. Again, you've got the European Union, the E1 and the E5A open signals. So this is sort of where the satellites appear, even though some of them are doubled up in terms of signals. So that's with the Huawei smartphone. I haven't got an iPhone, so I don't have it. But apparently you can download that app from the App Store and run it. What are you actually measuring? Sorry about this method. We'll put it in an equation. But basically, it's a one-way system. Satellite transmits. There's no message going back to the satellites. That's why you're able to get an unlimited use from the ground, because it's a broadcast system. It's a listen-only system. The user does not have to expose its location through a transmission. But they have to have a clock, reading clock, versus a clock in the satellite. So we have to know what the time of transmission. So how do we create a time of transmission marker on a sine wave? That's where your code modulation comes in, because it creates unique combinations of zeros and ones, which are aligned with, if you like, the tick-tock, tick-tock, tick-tock. And not only the tick-tock, tick-tock, but also the time as an absolute quantity, time of transmission. We also need to know the location of the satellite. You can't do space-based, satellite-based positioning without actually knowing the satellite position. You can invert the problem if you know where this location is, and that's part of what goes on behind the scenes to operate GPS and GLONASS or Galileo or Beta. Is you have a network of ground receivers to track the satellites, to determine their location, their coordinates in that reference code. Upload that, which then comes down to a user who doesn't know where they are. They find out where the satellite was at the time of transmission. So they get that 2 bits of information. They match it against the time of arrival. And of course, there is the transmission path, the propagation. So when you write that equation down, this is one simplified form of an equation, you will start to see that the basic measurement is time of arrival minus time of transmission times the speed of light vacuum. It's called a pseudo range rather than a range or a distance, because this clock and this clock are not synchronized. If they were, then it'd be a range. Then this would be the true distance if you compare those two clocks if they were in synchrony. But they're not. You have, right, okay. In this part here, the geometric range, you have basically Pythagoras. You've got the coordinate x, y, z of the user, the unknown coordinate. You have the coordinate of the satellite, which changes with time, of course. So you have to be very sure that you know where the satellite was at the time of transmission. So this is your model of distance. So this is your measurement of distance. This is your model of distance. And there's a whole bunch of errors. Noise, tropospheric delay, atmospheric delay, errors in the signal in space range error, which is essentially orbit and clock. So the error in this clock plus the error in this quantity going to here. And then there is the error in the user clock. So you've got error, error, errors, errors, and basically the designers of the algorithms are about how to accommodate those errors within the specifications of the user requirements and ultimately governed by the noise of the measurement itself. So at that point, you model something to a millimeter. If this part here only has a resolution of a meter. Okay. So the estimable parameters, the core numbers that we are interested in is x, y, z, and time, or time correction to the receiver. And therefore, a GNSS receiver is the most accurate clock that you can carry around with you. Right? Far more accurate than any Swiss chronometer. It's a lot cheaper. Range 0 to 1. I don't think I want to show you that. What is interesting is that, as I said, the design of the algorithms is about driving down the biases and the errors. There are some biases which are correlated, and you can do tricks to remove them, or you can model them, therefore reduce the size of the errors, not necessarily to 0, but bring them down. You can have operational procedures where you have cancellation of errors. A whole bunch of little tricks, and basically, you know, surveying in Geodesy over the last 35 years, certainly since I've been involved in GNSS, I've been all about finding new ways of squeezing these biases and errors. So let's start with your basics, which is the idea that you need 4 satellites to give you 3 components of coordinates and time. Therefore, you need 4 pseudo-range measurements straight out of the box. Your smartphone does it, and how they did it back in the 70s and 80s, 1970s and 1980s. How accurate is it? Current pseudo-range based signal point positioning, sorry about the acronyms, are at the meter to decameter coordinate. Decameter is centimeters, not decimeters, right? No mistake. Sometimes you see it down to a meter, if not better. Sometimes due to really difficult errors, principally multipath, it can be 10 meters or less. But the accuracy of time is about tens of nanoseconds. That's why I said it's a very accurate portable clock. It's not a laboratory clock, obviously, but it's a clock, not a frequency counter, not a tick-tock, nothing. It's a clock. Absolutely amazing. And that's why GNSS is so valuable for synchronization of telecommunications networks, electricity distribution networks, and so on. Because the time that we now share, you turn on this, right, and we all share the same time, your computer, comes 2 ways, either through the 4G or 5G network itself, through its timing, but it is not as good as GNSS. Okay. Coming back to this example here, my colleague who did this experiment with his phone in Queensland, Brisbane, compared an old phone, the red dots, because he basically held a phone out on his backyard. Yes, a swimming pool under there. Look, solar cells. We tell the orientation of the house. And the green one, which is the dual frequency. So immediately, two frequencies is not just more numbers, more measurements. It's also a way of handling one of the important errors, which is the ionospheric delay on GNSS signals, which could be up to tens of meters in extreme conditions. Okay, so dual frequency multi-constellation. That's the new acronym, dual frequency. This is GPS and Galileo is now sort of, L1 and L5, dual frequency, two frequencies. Multi-constellation meaning having basically receivers over the head and all of those. It's still only accurate a few meters because the other major error is multi-path. The signal not coming directly from the satellite, but actually bouncing off buildings and coming indirectly to the receiver antenna and being mismodeled as a line of sight distance as opposed to a true, the true path of this traverse. So that's your base level, right? Okay, so if I was giving this class UNSW, as I would have, take 5 lectures to get to that point. I obviously missed, how to actually make the measurement. What about the datum? Each one of the errors, where do they come from? How can you model them? How much variability is there? Then I'd go through all the geopolitical stuff, which I love. Talk about geopolitical stuff. That's one of the things that I enjoy is sitting in a room to listen to the people who paid for this stuff justify the reason why we have so much waste. I mean, obviously don't use that language because you listen politely and you listen to the Russians, you listen to the Chinese, the Japanese. Well, basically the Japanese don't trust the Chinese. The Koreans are building a system because they don't trust the Chinese or the Japanese. I mean, the Brazilians are, when is it too many? Because we could actually have a situation where we have jamming of each other's signals, which creates some motivation to improve the signal coding, modulation to make that a bit more immune to cross interference and so on. So the best on augmentation, how do you improve performance? Improve accuracy. Right? I mean, there are, as I said, there are other augmentations, reliability, being oblivious to spoofing or jamming, being protected against that, and so on. But let's start with positioning, because that's the sort of thing that interested me. So we can distinguish now with our standard single point positioning with precise positioning, so PP. We're now entering a new world of PP. Now, we also know that there's a basic or open service for each GNSS that is free, but there are several types of PP augmentations, and I've got here 2 types. One is called differential, the other one's called absolute. And each of them requires slightly different user equipment, infrastructure, communications, and so on. Sorry, this is a mind of its own. Now, I refer to these augmentations as services, because somebody has to pay for them. So some of them are free, some of them are not. Different users typically use different augmentation services, so they're industry sector based. So the marine, intelligent transport system, surveying, aviation tend to not trust the other augmentation services. So we have now also a waste, like speak about it as waste, even at the ground infrastructure level, service level. So that's what that. And augmentation services typically are independent of the signal provider. So we're talking about signal providers and service providers. Most signal providers, except for GPS, also provide enhanced services. One of them is, of course, the military. That's a secure service, an encrypted service. That is an augmentation that the average user cannot access. Most of the GNSS and RNSS also provide additional ability to get higher accuracy. Now, how do you get higher accuracy? You've got to push it below the meter, right down to the centimeters. And, you know, the more accuracy you want, typically the more expensive the receiver is and the service price goes up. Okay, so that's an interesting correlation. Now, I've got here 4 modes of the precise positioning. Unfortunately, I'm going to have to go through. How much time have we got? Where did I start? Well, probably going to take a little bit longer. Okay, more acronyms. We can do pseudo-range-based local differential, that is to run your user receiver, but also have a nearby reference station or base station or whatever. It's going to calibrate the errors and somehow and communicate with the user and enhance their accuracy. Doing it by terrestrial links, you can do a local area differential GNSS. Typically, you would access this communications via basically mobile telemetry, mobile telephony, sorry, through a data service. Wide area differential GNSS, as the name implies, is have fewer reference stations, but each user then accesses the surrounding reference stations in a sort of an integrated way so that they get a correction, but it's based on a wide area. And that can be delivered by a SATCOM link as well as by a terrestrial link. Once we get into carrier phase or CPH, we'll see why that is a benefit. We again have the 2, the differential, but this time we also have the absolute or point position. And curiously it's called PPP, precise point positioning. It can be done in real time, post-processed, differential using terrestrial links. We'll see how these have evolved separately and how these days this is becoming an interesting alternative to differential positioning. Carrier phase. As I said before, we have, if you strip away the code, the modulation of the zeros and ones that create the ability to transmit from the satellite to the user information, like the orbits, right, and the time of transmission. You strip that off, you still have a carrier phase, the sine curve. And it's L-band microwave frequencies, so these are the sort of wavelengths from GPS, L1, L2, L5, 19, 24, 25, 25. The problem is the sine wave looks exactly the same, so it's not, it doesn't have any information. So the information has already been stripped off. But you can't make an absolute distance measurement because what you have is an unknown integer n times the wavelength plus a fractional part. And this is the part that can be tracked. You lock on, you make a measurement of that, and then you make a measurement of the change in the number of wavelengths, but you never have information initially of the first number of unknown wavelengths. Remember, we're talking about distances at least 20,000 kilometers with wavelengths of about 20 centimeters. So as the Americans say, you do the math, a lot of wavelengths. And that n, remember the satellites are moving at about 4 kilometers a second. And the line of sight change, I think, is about maybe a kilometer a second. A kilometer a second, how many wavelengths that is. So it's pretty rapid change in the numbers. But still, mathematically, we can link over time and between satellites and between receivers to basically, through the 1980s, civilians, this is civilian innovation, by the way, because the military were not interested in carrier phase. The civilian market wanted high accuracy, and it came from carrier phase. But the negative was we didn't have the N, the ambiguity. So the positive is it's a low noise measurement, right? We can make that measurement This is 20 centimeters. We can make that measurement to a few percent. So we can make that measurement to literally millimeters precision. But we can't find the distance to millimeter accuracy. So the challenge, therefore, was this big. Lots of PhDs were developed in the 1980s, perhaps even into the 1990s, about resolving this challenge. Now, of course, we've got commercial products that can do that. So clearly, that research has gone and created the capabilities that we now take for granted. So what does a differential carrier phase scenario look like? You have a user, you have a reference station, part of a network. These might be tens of kilometers apart. I'll show you one at the moment for Switzerland. And somehow there's a communication meter here. Of course, if you want to do it in real time, they can down through your telemetry. Basically, they just push it out onto the internet, and you just access the internet wirelessly. Now, so for some it's free, others you might have to pay a subscription. And all the software is in here to basically handle what comes across here, which could be these raw measurements or some variation of that. This receiver makes these measurements on multiple frequencies, maybe on multiple constellations. The maths has to work out the end. Out comes something, even in real time, that is centimeter accuracy. And you can move, and you get centimeter trajectory, as you might need for precision, civil engineering and precision agriculture, or for scientific purposes. You keep it bolted to the bedrock. Okay. The very first statement, 1,000 times more precise as a measurement than pseudo range. So clearly, we want to harness that advantage. Differential makes possible far higher relative accuracy than absolute accuracy because of the spatially correlated biases. We didn't talk about that. I think I wave my hands to say, if you have multiple receivers operating, listening at the same time to multiple satellites over time, you got correlated errors in clocks, in orbits, and in propagation delays. The coordinates end up being determined relative to that reference station. Not a big deal. Just got to make sure that we know those coordinates of those base stations in the correct data. Another acronym, why not run it 24 hours a day permanently, continuously operating reference stations? Then you can go out there any time of the day, as long as you paid up your subscription to Swiss Topper or whatever it is. You can do your survey and not worry about the infrastructure. Right? This is important. We've got an incredible investment in this ground infrastructure to make it possible for you to take advantage of that precision, that precise measurement. So it could be government run or private. In many cases, both. Areas of operations may be quite small or they could be quite large. Continent-wide, as opposed to maybe even a project, engineering project, construction project. Constraints exist on other constraints. The constraints are really about this ambiguity technique, ambiguity resolution technique. And of course, then you've got different levels of sophistication in terms of the software, which is the observation model. Science is always doing things 1,000 times more precise relative to the distance that we're dealing with, compared to a commercial press the button and get the answer type implementation. So this is something I pulled off Swiss Topper's website. Lovely, even spread. You can, better than me, sort of estimate the distances between here, a few tens of kilometers. If you look at Europe, this is only one version. I mean, there's a far denser networks, but this is a scientific network in Europe. Curiously enough, it extends, there's even one here, but that's been turned off the latest I heard the last few days. is that the Russians are not helping with scientific cooperation anymore. This is one of the collateral damages of the Ukraine conflict, is that we're no longer looking globally ground infrastructure. This is, I think, now 2021. This is a guy at the University of Nevada who actually processes all of this data. And we're talking about over 10,000 receivers. And if you think that some of these are investment of at least 50,000 euros because of where they're located, supported, wonderful, stable monuments, communications backup, power supplies, etc., and a receiver that costs at least, maybe $10,000, 10,000 euros. That is a huge investment by governments, not by the military, right? Not by the signal providers. This is an augmentation. Remember, you take what is given to you for free, signals. You've invested, you meaning the civilian world, maybe for science. These people here are obviously interested in earthquakes and measuring cost of motion. Here we're interested in supporting agriculture, which is why we don't bother about the deserts. Nobody's working up there. Nobody needs coverage. Russia has a lot more than that. China has, something like that density. But we can't get any of those stations out of there. Africa, unfortunately, is a white spot. North America and Europe clearly are saturated, I think is probably the correct word to say. So that was differential. Now, if you take away the reference stations, or look at them from sort of separated point of view, and you're working here, if you can not have to worry about having a close reference station, so you just got private reference stations, you can use this mode of positioning called precise point position, multi-frequency carrier phase and pseudo-range measurements. But now you need additional data. Certainly you need accuracy of the orbits, the centimeter level. I didn't tell you that before, you happily did position of centimeter accuracy, even with satellite orbit errors at several meters. How? Well, as I told you before, there's a certain amount of cancellation of errors in differential position. So you need this stuff that doesn't come from the signal providers. This is an augmentation, but it has to somehow get to these users, marine, land, or deformation monitoring. That's what this made out of. It could be real time, or it could be post-process. Accuracy, decimeter to a few centimeter accuracy. And there's also an issue about what we call convergence. There's a price to be paid for removing access to the nearest reference stations. Right? This is, again, a trade-off, engineering trade-off. So what do we know about PPP? Main benefit is less density of the core stations, very attractive, less investment. Who wouldn't like that? Main difference is the measurement model vis-a-vis the differential model. So there's no between receiver differencing, so you need to find another way where previously it was very easy to mitigate or eliminate biases which are spatially correlated. So you have to do that by bringing in, by bringing in a substitute for what is normally transmitted on the satellite. So it's got to come by another channel. Right? We'll talk about the various channels in a short while. We have to eliminate or model the tropospheric delay. We typically use dual frequency. And we have to estimate tropospheric delay. There are different approaches. You require some caused infrastructure. Well, okay. Like that. Perhaps a couple of hundred reference stations, even down to 100 reference stations, to be honest. So you can create precise orbits. Slow convergence, I already mentioned that. PPP combined with satellite-based communication downlink is an attractive option now, which I'll just talk about. This is the International GNSS Service Network. It's a science network. Many of those stations have been established for 30 years. So that provides us with a continuity, because what you also have to appreciate is some of these continents are moving apart by up to 7 to 10 centimeters a year in continental drift. So when we're dealing here with centimeter accuracy, even our reference stations and our reference frame has to have a stability that is a fraction of that. Now, what's a space-based augmentation system? It looks like a PPP, which is why I told you, marrying the two concepts. But it came from aviation. Basically, they wanted, through this link, through a communication satellite. So this satellite is not part of the GNSS constellation. It has a ground network, it's involved with that, and it transmits 3 types of information: the corrections to make higher accuracy, extra pseudo range to improve availability, and most importantly, integrity messages. Tells the receiver in the aircraft, tells the pilot basically, when not to use it, when they suspect something is wrong. So you have a ground network that basically monitors the health of the system, but ultimately is an augmentation to GNSS. Currently, ICAO, International Civil Aviation Organization, only has certified L1 on GPS, but ultimately we're also they're supposed to consider. Aviation moves a lot more slowly than the rest of the world. You still don't have only sub-meter accuracy, because for landing of aircraft, or aiding the landing of aircraft, you don't need centimeters. But what you do need is to be absolutely certain that when you're flying through those clouds, down the glide path, until you get to the decision point, to abort or to continue, and you hopefully the visibility comes in, that you are actually at the right end of a runway, because it's too late then to make a decision, a false approach. So they're interested not so much in the accuracy, but really, can you trust the coordinates? Can you fly down the glide path, even fully automatically? What we should know about that: design for aviation, not only integrity implemented as alert messages broadcast to users. So I told you, it's a significant augmentation. It costs almost the same as the GPS. Why they couldn't build it into it in the first place? Again, it's because the military funds the signals, the users have to fund, how to make sure that you're trusting what you get. We have regional whoops. Okay. That's free to air. So in fact, the smartphone can actually decode these messages. Can attract our non-attention. Now we add a few more acronyms. So you saw this before. Wide area augmentation systems, that's US, Japan, European.
Geostationary navigation overlay system.
Right. GAN is the Indian. Remember that acronym? That's the Russian one. This is the Chinese. It's the Korean one. Even this is the Australian. And all you need for that is this communication satellite, right? You still use basically somebody else's GNSS. You pay for a couple of geostationary communication satellites, dedicated, because if you want them certified for aviation, you don't want them to go offline, right? And then you'll need the ground network in that area, here, 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 or here. That basically monitors the atmospheric conditions as well as the integrity of the signals as received by users in that area of coverage. So these are all regional focused. So the future navigation satellite systems will likely be in the SSA category, but we improve with more generalized user focus than current first generation systems. I would draw attention to this Geophysics and multi-constellation. This is an example of a chart in terms of deployment here, And what you have here is the GNSS, and down here, in parallel, notice L1, L5, the various constellations. And some of them come from the signal providers. In the case of the US, the Federal Aviation Administration runs a separate communication satellites. Europeans, it's run by the same agency that runs Galileo. The Russians, I'm not sure of. The Chinese, again, integrate things because it all runs on basically the same banner, they're all military. And they all have to be free because this is what they agreed to. Now, this is the way that you would implement it if you took, instead of SBAS L1 pseudo-range, you now add the full suite of carrier phasing pseudo-range to get this level of accuracy, right, with PPP, but communicating with this receiver directly through an external communications channel. Now, this could be free or it could be a subscription. It could be on the same frequencies. The L-band frequencies, it could be different. The S-band frequencies, who knows whatever. But basically, they're sending you this augmented information to implement this in a more seamless way. Hey, but why stop there? Why have even an external communications satellite? Why don't we actually use the satellites themselves? Now, of course, that can only be implemented if it's a signal provider, because they own those satellites, right? So the Russians are not going to say, oh yeah, Switzerland, you can just transmit stuff on our satellite, on our 24 satellites. No, the Russians say, we will transmit it. So those provided by the signal providers, have access to basically putting it down on the same signal as you're sending the other messages and on which you're making the measurements. So it's an additional modulation. And you may even want to charge for it. Actually, what's good is Galileo decided about 2 years ago to make it available for free. So that forces the hand of the others who thought there might have been a business case to ask for the users that access this additional augmented information to charge for that. So we're still looking at decimeters, still a few centimeter accuracy, it's a precise position. Still got a problem that it might take quite a few minutes to get to that level of accuracy. So it sort of comes down to 1 meter accuracy down until it reaches the point of diminishing returns, and you say, okay, after 15 minutes, 20 minutes, it's fine. Not good enough to compete with differential. So, some smart person decided to marry the two concepts. Use a local reference, local continuously operating reference station network, which typically does RTK, real-time kinematic. Marry it with the SBAS type transmission of this enhanced or augmented information to create basically the receiver, people who develop the receiver, hardware and software, to basically either have to find a way to get access to this, because this stuff comes free of charge, so to speak, although they've got in all cases. You enhance it by more additional models of the biases. Doesn't improve the accuracy very much, in fact, at all, but it can lead to what we call faster convergence. So now it's compatible. It's a reasonable alternative to differential position. But I have to ask myself, I'm skeptical because I'm saying, well, the reason you went to PPP was to get rid of that. Now you still need the Swiss type O, for example, cause network. But you now have to deal with signals that you have no control over. You have no control over that. And you comes out in a reference frame coordinate system defined by these people who determine this orbit. Fortunately, Geodesy sort of sorted that out. Time to first fix. Unlikely to ever match time to first fix of RTK with time kinematic unless local. Look at that, I can write a whole sentence with almost with just acronyms. And then I'm with but this reverses one of the major advantages. As I said, I'm a skeptic, a little bit of a skeptic. Being able to implement it in real time via an SSA type downlink is attractive to commercial service providers and some signal providers. Augmentation services can be decoupled. So if you are concerned about sovereignty, your PNT capability, this is also one way of justifying the cost at a national level by saying, well, we will be able to control, what gets transmitted, because we can't control what gets transmitted through the satellites that belong to the GNSS providers. We can control the communications, other communications. The problem is it destroys that elegance, because you now need a more complicated receiver. Can you fool that receiver or encourage the manufacturers to implement tracking of pseudo GNSS satellites with the appropriate decoding of messages and algorithm enhancements? That is still, as far as I know, hasn't been solved, but I know that I keep pushing people pushing people in Australia. Tell me how you're actually going to encourage, Leica and triple manufacturers to build you a receiver to support your servers, which all sounds wonderful in theory, but how's it going to run commercially? Okay, the last few slides I talked about users. I'm not going to. But what I'm going to refer you to is two documents, which actually they're free and they're downloadable from the what formerly was the GSA, European Global Navigation Satellite Systems Agency. Every 2 years they produce a market report, covered trends in the market, broke down the market into different segments, try to put a value to it, projected forward 10 years, sort of market surveys and so on. Now, the reason I haven't shown you the latest one is because there was a subtle change that happened with that last report. I'll come to more. And this, in one slide, summarizes what they claim is the 10-year market, right? 2.5 thousand billion, I guess, euros. Yeah. The majority are the road. Imagine everything from your simple navigation systems to pricing of roads to truck monitoring, tolls, etc., and consumer solutions, all your location-based services, mobile phones and search and tracking and telematics. And goes up many labels. What's interesting is that this is the group that I'm interested in, the other, because they're the ones that deal with higher accuracy. Road consumer solutions don't need augmentation. They can basically use the stuff out of the box. Oh, the Internet of Things is also thrown into it. This is a group, when you break it down, seems to be a significantly smaller group. Oh, the numbers might be completely large. Geomatics is also that. And the proportions vary from country to country. But my question is, whenever anybody's done a true market survey, it's not the quantity that's important, it's the quality. These people here are using receivers that cost less than $1, and they're paying $0 for using it. And the value that they get from, say, displacing paper maps with one of these looks impressive because, you're talking about 1 billion of these. Several billion. These people, for example, rail, or maritime, or agriculture, their receivers are at least 1,000 times more expensive. So you can't compare apples to oranges. It's more like comparing a grape to a watermelon. I don't know if you've heard that expression, apples to oranges. Well, I consider it sort of grape or watermelon. So the value and the benefit in, say, agriculture, of cutting the fuel, because you're now controlling the machinery much more tightly, environmental benefits, the economic benefits. You work day and night, you can automate it, take the human out of the loop, the whole bit. That is inflated by another 1,000. So I honestly think these people in Brussels, no, not I think they're in Cardiff, who do these numbers, as I said, I'm really comparing grapes with watermelon. And the value is much higher if you look at the benefits of the economy and the environment and society. Now, if you look at that document, these are the different chapters. It's really quite interesting to read them. Nothing on space. But there was a section right at the very back, Emeritus Special GNSS for new space. And it talks about some of these applications that didn't fit into that other category. Now, this is 2019. In 2022, right, issue 1, they combine, unfortunately, GNSS with Earth observation because they created a new monster called the European Union Agency for the Space Program. So they married Copernicus and Galileo, if you like. Copernicus representing the sort of suite of Earth observation, missions, and GNSS, of course, the Galileo and EGNOS. So you can download that report. But it actually tries to look at each of these market segments now, not from the point of view of GNSS only or Earth observation only, but sort of linking the two, because obviously, I guess they want to satisfy their masters who pay. And there is a section on space. So when you look at, they've got different color for Earth observation application, GNSS application. It's unfortunate in the space application, there's no Earth observation. You don't observe space or space. Because actually GNSS can do the sensing of, for example, the atmosphere. And they've talked that, and they've got multiple pages within that chapter, but at least it's now, you know, looks at key trends, user perspective, industry, recent developments, future market evolution, European systems, and so on, so on. Okay, this is the last slide, because I truly tested your patience. I'm not sure that there's anything there that I have not already said, except possibly down here emphasizing trustworthy positioning, not just improved accuracy. Alternatives to GNSS, because we can see how vulnerable that is. I mean, the aviation community in Finland and in Estonia and whatever complain about the fact that the Russians are jamming. You fly over the Middle East, it's jamming everywhere. You go to China, there's jamming. Unfortunately, they're not mission or life critical applications because they've got alternatives. They can use just their inertial systems and aircraft. But worst case scenario is this is one of your cyber attacks. It's not just done through the computer channels. It's actually taking out your infrastructure that supports precise and trustworthy position. So, unfortunately, there is no good alternative to GNSS because it is cheap, very free, ubiquitous, global. It's only the apps that, so you go to China, you can't use Google Maps, but you can still receive the satellite signals. Just you can't have access to the servers. That's just an example. I'm not criticizing any particular country, but geopolitics is tied up with this, just like a lot of space technology, space industry. It's not always rational and logical, like you think, because it's new and cutting edge. It's still subject to the same old jealousies, quirks, business, issues monopolistic practices that any other technology is subject to. Thank you very much for your attention, and thank you for the team for inviting me to speak. I hope that you found it interesting. I think some of this stuff you probably haven't seen presented this way. And I've also shown you that there's no one single solution. What we have is that with each additional capability, we basically open up a plethora of interesting questions and alternatives. So what used to be just black and white GPS was gone through to Technicolor. It's now moving almost to holographic, and ultimately it's going to be VR and implantable. So it's exciting, and I hope some of you are interested in continuing to study geodesy. Thank you.
Okay, thank you very much, Professor Rizos. Now the talk is open for questions.
Well, I propose, as we're already a bit late, so I think if you have any questions, you can come to me personally. Well, and the others will have to keep or get a train. And that's it. Thank you very much.
Thank you. I'm available if you have any questions. And I'm sure that my colleagues here will also be able to answer those questions.
Yes. So you have those reference points. I guess they know the location, GPS coordinates, and they send them to the users, like my phone, for example.
Yeah, one implementation, simplest implementation you can imagine is that you know your coordinate, it calculates the coordinate, there's an error, it transmits the error and says, okay, if my error is this much here,
yes,
you know, it'll be the same at your location.
Right,
now, of course, there's a whole bunch of assumptions, but that's the simplest level, and that's basically how they stumbled upon it in the 1990s.
How does it know its location? You can't use the GPS to find the location of the.
It's been determined by prior techniques. It might be done by conventional surveying. Right. It would be done by GNSS, by Geodesy, who do it by also determining the orbit at the same time, or in a bootstrap fashion. There's a whole bunch of geodetic techniques, but ultimately you can get the coordinates of your reference station to sub-centimeter accuracy and track it with time. As it moves, you don't want that to drift. Right? I mean, Swiss topo now is all about it.
It goes beyond that. I mean, one thing that is very nice from a conceptual point of view is the virtual reference station. And how does it do it? So you are here with your receiver, and you get an approximate location from a very basic GNSS data. Now, this has nothing to do with satellites, GPS, or whatever. You deal with the service.
Maybe I can ask you a given that you have so many parameters, how to define the passes?
The server, il questionne les
well, I mean, in this context, general sense, public understanding. That is, if you take out satellites that works, right, you have failures. Now, if you have failures and you don't know they're failures,
avec
then
un
you can have
récepteur
a solution. So,
autrement dit,
and that's where the
vous
aviation
obtenez
was really
les
concerned.
mesures
That's integrity. That means you can have an awesome
Excusez-moi,
ça
vous sert
parce
qu'il va traiter
right? Some people don't trust it. Or the
it's
robust. That is
pour votre récepteur, c'est comme si vous aviez
but you have still robust, not trustworthy. Something glitch. system error.
But
System error, upload. I happily get my 6 hours that upload. It was shifted but everybody noticed that. Right? A million users. The Russians were not, but again, the system was robust because for the critical applications they had access to the other signals and they just deleted them, ignored them until they told them it was fine. So the system is robust individually and but it's still not trustable that when you've got a critical mission application or safety of life application like aviation, that we need these to be at 99.9999969. That's sort of the integrity. And that's what